Yeah, my name's Matt Raso-Barnett. I work at DDN. I'm a senior systems engineer there. And yeah, I'm going to give a bit of an update on where EXAScaler is at. So yeah, I've got quite a few slides as well. I'm going to try and race through these a bit because I think fairly short on time. Just first of all, for people who don't know about DDN, who we are, DDN, we're a storage company, particularly focused on high-performance storage, and more recently, obviously, around AI. This slide, we're involved with a huge number of the largest, AI, HPC system deployments in the world. There's a number listed here. AI has obviously really taken off the past few years, and it turns out to be very good workloads for Lustre, and EXAScaler is at the heart of a lot of these major systems. You can see one here. In fact, I think the next slide, one of which NVIDIA are deploying this and power a lot of their major systems. So NVIDIA EOS was unveiled at SC earlier this year. So that's their latest generation AI supercomputer. And that is powered by EXAScaler as the high-performance storage layer. So, EXAScaler, Lustre, EXAScaler is our, is at the heart of this and is our kind of productized version of Lustre for these systems. So I'm going to skip on just a bit here so we can talk a bit about some of the new things in EXAScaler. But first of all, for those of us, or those who haven't kind of come across DDN, we also sell our EXAScaler solution as an appliance. So, we will provide a hardware all-in-one system that you can buy from us, plug in, and in this diagram here, in fact, you can see just this 2U system here is completely self-contained parallel file system. So there's been a lot of work done at DDN over the years to really kind of simplify the whole stack down so that we can now sell this kind of fully compact system that contains all of the pieces needed to run a parallel file system. So in this 2U box, you've got 24 NVMe drives, you've got 2 controllers, fully redundant through all of the HCAs, and there's actually 4 servers that are fully virtualized within there. So, all of your OSS, MDS, they're all contained within that box. And that single 2U unit itself can do like 90 gigabytes a second read, 60 gigabytes a second write, for streaming write throughput. So it's a very well optimized, efficient system. And they can also, we can scale these out completely linearly, so we can keep adding systems and scale that, that throughput performance, as far as you want to go, really, like, how big of a system that you want to build. So, yeah, there's, a graph going here showing kind of that linear scaling for these systems. If you have like 12 of these AI 400X2 appliances in a system, and then the x-axis here is as we go up through those systems, you can just see the performance scaling linearly. And this turns out to be really important for AI. I think it was noted earlier in one of the panels, right? One of their most important workloads for them is doing checkpointing, right? Because if you're building this massive NVIDIA AI supercomputer, you're doing training workloads on that, but then you're pausing every so often to then write out a checkpoint before you continue that training. That's a massive cluster then that is not doing compute, not doing workload, all sitting idle for I/O. So, having very fast write throughput at that point is obviously important in that overall system efficiency. So this is something where Lustre is, really showing its worth, and this is why it's, or one of the reasons why it's very popular for these systems. Okay. So that's sort of the intro. I'm going to just try and do a bit of a whistle-stop tour through some of the developments in EXAScaler recently. So, you'll recognize a number of these from Andreas's slides. So, with EXAScaler, This is our DDN's like productized version of Lustre. So there's a number of features that we're developing and that they'll be available within EXAScaler, such as client-side data compression. So this is available now within EXAScaler. So this just came out in our most recent release in 6.3.1, which is in the autumn this year. And yeah, you can use that today. So as Andreas mentioned, this is really interesting for users. It's fully client-side, so we're leveraging all of the compute from the client CPUs to perform the compression, and then sending that compressed data over the wire. So saving on network throughput. There's ability to choose different compression layouts. So as Andreas just mentioned to one of the questions, that's fully configurable by the user. So you could set that on a directory. You could even set it as part of your workload, right? So if you're running like a workload management system, perhaps you initially write the data, but then you could, do an LFS migrate with one of these layouts or copy it to a different directory later to, compress it and save up space, or, do it for a subset of your data. So I think that, configurability is very powerful compared to doing that on the server side. And yeah, I've got some more slides on compression. So just to that point about configurability, we support multiple compression algorithms. We've even landed the Z standard compression algorithm. I think that was developed at Facebook, one of the more modern ones, and that turns out to be a really great combination of performance and compressibility. But you have the choice, and this gives you as the administrator or you as the user the ability to tailor this compression feature for what you're trying to do. If you want to, have something on all of the time for general purpose usage, you might want to use like LZ4 Z standard, which has that good combination of performance and good compressibility. But if you're just trying to repackage some data that you want to keep around, but is more for kind of archival, long-term storage, then you could use, one of the higher compression levels of these algorithms or a different algorithm to do that. So the choice is yours. I've got kind of a graph here of some data. It's just showing compression ratio on the y-axis. So, the higher, the more compressible. I mean, the data used is itself very compressible data. So, it's sort of showing like a best case here, which is why you've got such very high compression levels. It's all kind of textual data. And then like a log scale of write throughput on the x-axis. So this kind of top corner is like the ideal, as you're getting, the most performance, but also a good compression ratio. But this is really just to sort of show, there's lots of kind of choices of the algorithm that you can use. I'll skip on. I mean, yeah, there's plenty of testing that we've done with different data sets. It varies a lot by compression, of the compressibility of the data itself. But as Andreas mentioned, one of the new features that has just been added to this is to detect the compressibility of the data as it's being compressed, and then disable compression if it's finding that that data is already, or is incompressible. So if you're, writing out like a compressed BAM file or something that's already been gzipped by the application, then it will, detect that and stop trying to recompress it. Okay, some other features, I'll just move on here to, another one that you might have seen at previous presentations is a feature that's been in EXAScaler for a while now, but called hot pools. So there's some discussion on the panel earlier and about the usage of like flash and disk in systems. So, things like burst buffers, tiering. Hot pools is our answer to that. So with hot pools, you can combine a hot flash, or a flash layer or flash pool within your file system, and then have another tier within the same file system, perhaps using hard disk drives, or more recently, we now sell systems with QLC flash that is very, very performant actually, but has much of the same economics as hard drives. So you can combine those two into a single usable namespace, single file system, and let hot pools take care of the tiering of data automatically between those. So all of the user writes would go to that hot flash tier, but our hot pools policy engine will be migrating that to the cold tier over time, and then detecting, which files are cold and can then be, removed from the hot tier to free up space for additional data. Another feature also mentioned earlier, there was discussion about a lot of these AI systems now, these DGX boxes, for example, that are very popular. As Andreas mentioned, they combine a large number of local NVMe storage. So, with persistent client cache, we can make use of that, and this turns out to be very useful in certain AI workloads. So hot nodes is our productized version of persistent client cache, and we're able to automatically manage these local NVMEs for you. So, you as the user, you can set up a policy with this feature that, selects a certain directory, certain data type by various attributes, and have that automatically pulled in to the local NVMe for you. And then subsequent reads on that data will be read from the local NVMe. And this, as I mentioned, this is quite useful, particularly again in certain kind of training workloads as well. So in fact, I think there's an example on the next slide. I think NVIDIA have used this themselves with training. At scale, this can really actually lead to some really good efficiencies, because a lot of workloads will reread the same data. So if you can pull that into this local NVMe, then subsequent reads of that will not be selecting that over the network. They'll be coming from the local NVMe. So I think in this diagram here, the top diagram, these different kind of colors are showing like GPU utilization, network throughput, CPU utilization. So the kind of the sections here would be like a training epoch. So there's high GPU utilization while that's happening. There's network traffic while data is read in from the file system. And then there's a pause. This would be perhaps when there's like a checkpoint happening, and then the next training epoch starts. So in the top, typical parallel file system case, there'll be read of that data in both cases over the network. But if we use persistent client cache through hot nodes, we can instead have that first read over the network, but then when we move to the second training epoch, this blue bar here is now the NVMe throughput. So there's no more purple bar of the network. This is now all being read from the NVMe. So yeah, this is how customers can use this persistent client cache to accelerate those workloads. And yeah, I think this has been used by NVIDIA at scale. And I think when you at like the scale of tens of thousands of GPUs, which are some of these clusters now, this can lead to real like major efficiencies, like over if you're doing a massive training workload at that sort of scale, and you combine this can really lead to significant efficiency savings. Okay, how am I doing for time? I think I've got 5 more minutes or so. Yeah, okay, I'll speed up a little bit. I just, Andreas mentioned multi-tenancy. This is something of a lot of interest at the moment. I think there's, again, a lot of these, there's a lot of interest for a lot of major AI systems now to kind of be able to compartmentalize a file system into different, subtenants. So if, as these systems are getting larger, you're perhaps having different, different customers or different user groups that you want to keep completely isolated from each other, but serve from the same common storage layer, because it's easy for you to scale and manage a single storage system, but you want to then serve out that storage to each individual tenant, maybe over secured networks. So there's been a number of presentations, I think, over the year. I think there's even James Beals here. I know a number of you have probably seen some of these over the years. We're doing this at places with some of our customers as well, combining a number of the features like node map, subdirectory mounts to make that possible. But we're now starting to look at really bringing that into our management layer to make this really easy to do. And also, improvements that we can do as Andreas mentioned, even at the kind of network layer where we perhaps are in an environment where a customer has segmented that network into multiple isolated, VLANs, and we'd like to keep that isolated, but bring that through to the storage and give them a piece of that namespace. So, yeah, there's a lot of features within EXAScaler today to do that, but we're doing a lot of investment at the moment to really bring that together, make that easy to use for the administrator, easy to configure and set up, and yeah, easy to manage over time. Just quickly, yeah, there was a discussion, I think, about encryption. So EXAScaler has client-side data encryption, which, yeah, we've had that in EXAScaler for a while now, for a number of releases. So that is both file data encryption, but also file name encryption as well. So this is, can be really good in that multi-tenancy environment because this is all done at the client end. So a particular tenant can manage their own key. They are in control of, who then is able to access that data. Even the file system administrator may not have access to that, right? So it gives a much stronger level of privacy over other, encryption at rest solutions that might be done at the disk or storage end. So with this feature, a customer is able to take a key, they're able to mount the file system, and then unlock that data set with a key that they control. So if you, combine that with these multi-tenancy features, you can have a isolated part of the namespace for a tenant that is then also encrypted as well. This next slide, yeah, just on this point about encryption, I think as Andreas mentioned, this is really very efficient these days, and particularly running on the client side. So I think while there's an impact at the individual client level, so between 5–20% depending on the operation, when you're running that at scale with multiple clients spread out over your whole cluster, the performance drop will be much more negligible. So in this graph here, we've got like an IO500 run across 32 clients that we've done with encryption on and off. So you can sort of see fairly minimal impact when running at scale over multiple clients. Okay, and just, I know I'm probably running out of time. I'm just going to lastly just touch on some of the more management features of EXAScaler. So this is sort of the other part of where we're doing a lot of investment. As probably many of you know, this is an area where it can be quite a challenge at times for certain operations, deployments, updates, expansions. But with EXAScaler, we really want to take that complexity away. For many of the customers that we work with, they want this to just be bulletproof, no hassle, almost without having to have much in the way of someone managing that full time. So with EXAScaler, we've put a lot of work into this, and particularly one of the key features that has just come out in our most recent release, 6.3.1, back again in autumn, is online upgrades. So this is a major deal for us. So online upgrades is really, bringing the upgrade of the entire system, both the hardware, firmware, the Lustre software itself, and the entire image, in fact, that's running on. So your entire VM, all of the hardware, into a very easy process. It's really like reduced down to about 2 steps, effectively, and like a single command to actually run the upgrade. So taking away all of that complexity, making it very low effort for you as an administrator. You can just bring down the package, kick this off, and it will manage all of the orchestration of that. So all of the failovers of targets between hosts, that is all orchestrated for you. It's all done synchronously and with minimal impact for user I/O. So we're testing this all of the time now. We run this with benchmark workloads against it with heavy user workloads. So yeah, this is a major thing for us, and really simplify that for customers, whether they're just applying like a hot fix or they want to update, firmware or update to the latest release. Just make that a simple, easy to manage process. Okay, do I have a minute or two? I will maybe just skip on, there's a few monitoring bits, but I was just going to touch very lastly on, again, back on our appliances themselves, just for those who aren't familiar with them. So, this is, again, our latest controller platform here at the top that I mentioned, but we can also expand that out with now QLC flash layers. So you can see here there's controller units that you can connect up to that all-in-one appliance that I mentioned. So you can add additional capacity to a system very easily without adding additional controllers. And yeah, this is sort of the breakdown on our latest controller itself. So as mentioned, that's with 24 NVMEs in a chassis. I think you can get up to about 700 terabytes or so with the largest NVMe drives now. And in fact, yeah, I've got a slide here just showing these kind of building blocks that you can build up. So again, this is with our latest QLC expansion enclosure. We also sell disk expansion enclosures as well, which I think a number of you will run. And yeah, you can build some truly impressive high capacity systems, but with very, very good performance actually with these latest QLC drives. And just very lastly, last slide, sorry. Yeah, and there is also to come early next year in Q1, we're working on then the latest generation of our hardware platform. So that will be the AI 400X3. So that will see a major uplift in performance over our previous appliance. Okay, I will leave it there. Any questions?